see how many.
Okay, so since yeah, Kristen hits the recording, I should get started. So welcome everyone to the one word mathematical data science seminars. So today we are going to have Yatin Chow from UC-Riverside. Yatin Chow is an assistant professor from the math department at UC-Riverside, and his research focuses on applied math, including inverse problems, image processing, optimizations, HG equations, optical controls. So today he is going to talk about his recent works on continuous data simulations for two-phase flows. Yeah. So please take away. Yeah.
Yeah. Thank you. Yeah, thank you very much for the very nice introduction. So I'm Yatin Chow, and this is a work with Dr. Leung at City University of Hong Kong and Dr. Pakzad, who was actually one of my postdocs, and he's now working at Cal State Northridge. Yeah. So actually, before the talk, when I get the invitation, I was thinking about either talking about the mean field game inverse problem or this one, but perhaps this is a newer thing. Yet on the other hand, theoretically, it is not super surprising. So I will bring to what we are going to head towards. So one of the major difficulties we have is when we are given a PDE model, there are many things that you cannot control in life or you don't know about in life. For instance, initial conditions, for instance, boundary conditions. Those are problems that are in real life existing, but you don't really have the data. So for instance, I know some people might be doing those physics-informed neural network, which is also what one of my colleagues talked about last Saturday. And they were training a neural network to learn and using the fact that you can take derivatives of the neural network in a formal manner to obtain another neural network to train it. And by doing that, you do not have to go back and forth many times for solving an inverse problem. The way we do it, though, is we are going to do something that is looking like nudging. So we will kind of have some measurements on the with a particular model that is known, and the measurement of those entities just feed back into the system. So you are thinking about that being something like a system with an additional kind of control term or a nudging term. So data assimilation in here refers to this kind of trick, and is one of the ways to handle this difficulty. To be honest, it's not a super fancy way. It's a very kind of traditional, or I mean, something you can even expect. Like if you are given a model, this is one of the first way you can think of. The difficulty will lie in the cases when, for instance, your model is having some technicality in well-posedness or energy inequality. For instance, one of the work along this line would be relevant to Navier-Stokes, where you still have trouble in showing some of these energy equality, for instance, in some cases. And of course, inequalities is known for weak solutions. Say. Okay, and so the idea in here is that you would have measurements from a coarse grid, and you try to use the coarse grid information to feed back in it and give a more accurate computation of the model. And of course, there will be different applications, and so the idea is, suppose you are now given a dynamical system. So think about U prime equals to FU, whether F is like an ODE system, PDE system, or SDE, or like stochastic process. Now you want to do some measurements, you feed it back. And the way that was introduced would be that because we are working with a particular finite element model, element space, we can now take those interpolation operators and flip it and do that with an extension. Of course, there are still some tricky things. Some people can ask what this extension can be. In many cases, it can be seen normally just by the adjoints, but perhaps some people will ask, okay, if for instance you do things that are similar to DTM, perhaps you'll have harmonic extension and things like that. So there are these different choices of interpolation. I mean, there is these extensions you can use, but the idea is you can just subtract the.
Sorry, I think, are you moving your slides?
Yes.
Oh, I think I'm still seeing the title.
Oh. Yeah. Yeah. Wait.
Perhaps you can reshare me.
Okay. Is it working now?
Oh yeah, I think it was.
Okay.
Yeah, it slows down little.
Okay, sure. Yes. So yeah, that was the one of the difficulty I was talking about, and then this was the data assimilation that they were thinking about, just trying to put a feedback term, and the feedback term is some data fidelity or some residual term, and if the system is nice enough, you would hope that the solution will be close to the solution of the model that is the physically relevant solution that you can measure. And one of the works that inspired us of doing that is Azunali also and Titi, who do that with Navier-Stokes and Euler. I think it's incompressible. I forgot. Yeah, but it's Euler equation, and yeah. So incompressible. Yeah. So it's they were doing that with incompressible Navier-Stokes and Euler equation, and they got exponential convergence. And since then, there are many people who tried this kind of idea with many kind of model, and many of them are numerical simulations, but I guess some of them are also not difficult to show. One of the things that, like I said, that the tricky part will be that when you try to show things are converging, you would want the original model U prime equals to F having some nice properties. So what we will do is we'll take one model, which is the so-called multi-phase flow, and we'll take a look into why that is still having some sort of problems. Of course, numerically, you can just feed it back and you hope that it will work. But if you want to show some sort of convergence, it depends on the well-posedness of the model itself. Okay, so a comparison. So some people would think, okay, well, actually, you know what? This is just a dynamical system. Either you call it deterministic, stochastic, Markov chain, whatever. It's still a dynamical system, right? So you can say, well, okay, if somebody give you a noisy model, then one way you can think of would be a Kalman filter. And in fact, you can indeed have some sort of comparison, thinking about that instead of doing that, you now have a Kalman gain term putting back in. And of course, if you look at it from that perspective, then what you would do is you estimate, you will first get the covariance, and then you will estimate the new variance, and you fit it back, and then you get a posterior computation with the after you do the least square and you plug it back, and if you expect it stabilized, then you will get a Riccati type equation. In our case, though, we do not have a very complicated operator. We just have an extension operator given in the feedback term. So one can do some sort of these comparisons, but I guess this model is simpler. But I would expect that perhaps one can even improve the results by replacing that with Kalman type update. even though in this case we are not doing it in a stochastic manner, you can still view that. I mean, you can still view those operators as just some operators. You can do minimization and you can feed it back. But this is not something we have done as of now, but we can test it out later. So the idea of applying that to more complicated models will be to analyze whether this kind of method work both theoretically and numerically. And one of the models we are now testing is the multi-phase flow. And in particular, we simplify to two-phase flow because we want to both understand the theoretical behavior and the numerical computation. And theoretical understanding of multi-phase flow still boils down to two-phase flow or three-phase flow. That's one result for three-phase flow, but most of the time it's two-phase phase flow. And the first kind of weak result would be, result with weak solution will be around 2000 something with 2 to 3 different groups of people, Chin and some other people working with that. And then more complicated models like incompressibility, solid transport, and some other models are then considered. And in particular, one other work that's along that line, but is with free boundary condition, is David Ambrose work, and it's more focusing on the boundary integral potential to show the opposeness. So let's see why this is a interesting model to consider, in a sense that it is somehow on the boundary of well-posedness. It is well-posed, yes, because of the proof, but it has some tricky issue. And from a physics perspective, why do we care about multi-phase flow? Multi-phase flow comes from the fact that you have more than one liquid and they just mix together. For instance, oil and water and gas and this and that. And they have very complicated behavior. And one of the reasons, for instance, why one of my collaborators, Ted, who is now in City University, is working on multi-phase flow, is one of his previous advisors in Texas A&M and UT Austin. He was from there. The schools there focus a lot on drilling of oils, gas, and so on and so forth. And so they want many physically relevant computation to be accurate, so they really can drill at the right place, and then the crude oil bumping will be efficient. So this is more of a practical concern, and to be honest, one of his postdoc advisor at that time was an engineer, and so they care more also about the computational aspects. And the way they usually do it would be relevant to some discontinuous Galerkin model on these jumps. And so we were trying to do that with our trick of saying that, okay, how about we have some measurements on a crude coarse grade or some sort of measurements at some random places, and then we try to feed it back. So let us quickly introduce the model. The model has a saturation, a bunch of saturations, SIs. The sum of SIs are equal to 1, so they are between 0 and 1. And then there are some mass balance phase or mass balance transition model, where you will have some continuity equation. The T of some term equals the divergence of some terms. Now, what are those some terms? So you have a combination of saturations. In general, you can have all these phase transition or mass transition, depending on how you call it, Rij, and you would want these some terms to have some conservation law. And there's also a bulk or a formation volume factor in front. And then there's some function phi in front, which indicates the porosity. So they are not doing that with the porous medium power alpha, but they put a field phi in there to indicate this porosity. Okay, and then the divergence term will have something similar, the same phase transition or mass transition, some term, and of course also the formation volume, and then you will have the Darcy flow drift or the velocity vector. And this guy in here, as you see, many things are depending on S, but then there's something funny. There's something about P, okay? So P is what? P is pressure term. Pressure coming from the I phase. Now this pressure term is one of the things that are a little tricky because of course it generates, probably it generates the flow velocity as you will see in here. So V is somehow proportional to gradient P, okay? So that's not too terrible, okay? There are some tricky terms that we will neglect in our computation. We will make some assumptions to forget about the term to test whether our method are working first. And one of the things that are quite physically relevant is gravity. Okay, but we will drop that term. Okay, and then there will be also permeability and so on and so forth. So you would imagine that the Darcy flow vector is somehow proportional to gradient P if many other terms simplify. But of course, it is not entirely that. You will have this so-called relative permeability, which will also give us some problem. And we will show that in the case of two-phase flow that some of these simplifies. That's one of the main reasons we focus on the two-phase flow model. Because two-phase flow model, in the end, can give us some sort of degenerate ellipticity or parabolicity. We will talk about that. And then the piece will actually be governed by something called a capillary pressure difference. Sorry, not difference, but yeah, I always imagine that as a difference. So Pi minus Pj is some difference between the pressure term, and they will be governed by the capillary pressure, and that's governed by the saturation term of the I and the J phase. So this is quite a complicated system, and of course, like I said, some difficulty will also come from boundary conditions, which you will never really know in reality. So it doesn't work by directly setting some imaginary or perhaps very nice boundary conditions to have some nice computation. Theoretically speaking, though, you can indeed have several of these boundary conditions for analysis. Okay, so we first consider simplified model with the transition just as delta ij, then we just have this nice simple computation. So we also take some of them being constant. Then you will just have the following guy. So the dt of S will be given as the divergence of some nonlinear term acting on S, and then the gradient vector P, okay? So the nonlinear term acting on Si is where the trouble lies in. And of course, the gradient of P coming from capillary pressure, which is a transition between Si and Sj. Okay, and so if you simplify, in the case when you have two phase, because the saturation of one is one minus the saturation of the other, then you only have one unknown for S. So let us replace that with the one of S, and then you see when you sum them up, you will get something that looks more elliptic. So if I look into the first equation, I view, this is a kind of tricky. So if you look into these equations, if you look at the saturation term as being the unknowns, then of course this is somehow that looks like hyperbolic conservation law. Okay, yeah, with the divergence term. Okay, but now if we sum it up, because the saturation term sum up to 1, the dt term goes away, and then you will now get in the first equation, something that looks more like an elliptic equation, if you now kind of view the those K in here as known, and you now try to find the pressure term. But this is not that, of course. So we can have a well-defined notion of something called global pressure. Does it mean that it is not well-defined in three-phase flow or not, or more? The statement is not true. You can make some definition, but say that this is the case that you can have a rigorous definition, so you can have a nice analysis. It's not entirely true that you cannot have some definition of global pressure in three-phase flow more, but this, in the case when you have two-phase flow, you can make a very clear, rigorous definition so that some nice properties can pop up. Okay, so we now look into this structure. With S, it is still a hyperbolic type equation, but with P, you now get something that looks more elliptic. So if I can now replace the sum by something that is gradient of P, then I now get back to something that looks more like an elliptic case. Again, it is still not so, because the Kepler that depends on S will actually, in the end, we will see that we'll have some degeneracy of S close to 0. So you will have some tricky thing. Okay, but suppose we now have we now take the beta, okay, as minus of that larger than 0. Then you just sum these two guys, and then you take the product of that over the sum. Okay, so this is actually the harmonic mean. Okay, 1 over the it's the harmonic. Okay, and times beta, and then you integrate it. Then the tricky thing that comes up will be that if you define the global pressure as the integral from 0 to S of this weird combination, we get a nice equation. So perhaps you can think what is done above is a little artificial, but the end goal is to obtain the following pair, so that we now get something called the global pressure, and then it's such that you can now replace that with the respective term in here inside the divergence. Okay, and of course, then you will have also an additional term theta in there that is left. That's inevitable. Okay, because degree of freedom will have to match. So however you play it, you will get some term. Okay, then you will get a system like this. Okay, then things go nicer, because then you can imagine that you have something that looks quite elliptic. I mean, again, degenerate elliptic, and again, some people would dispute because it's a system. But if you forget about the thing depending on S, then it looks more elliptic. Then I have something that is more well posed. Okay, and then I can pass it to the second equation. Okay. All right, so that's one reason we look into the two-phase flow model, because then they have well-postedness result, and then we can go to the data assimilation. Okay, so some technical assumptions, let's just domain, but more importantly, you will realize that A4 and A6 are enforced. So in reality, we cannot make assumption of those Kepler and those beta very nice in a way that you just have linear dependence of S or just constant, because in effect those K's come from what? Those Kepler come from what? Those Kepler comes from it should be okay. Oh yeah, here. So they come from the ki's divided by mu's. You can somehow imagine those mu's as constant, but so are the ki's. Ki's, they are these relative permeability thing. So they depend on physics. We cannot just arbitrarily assume nice condition. And in fact, in many of those cases, they do not have linear relation. They do have some of these power laws, and the powers also depend on the physical nature. Okay, so this is one of the reasons this system is not so nice. But you will also then realize that by making some of these assumptions that are sensibly physically relevant, you would already be obtaining some sort of monotonicity of the operator theta, okay, depending on this. But on the other side, you will get a quadratic bound on the, the term in front. You will not get square. You will get 2 plus tau. So that will be an exponent, and that exponent is one of the main difficulty in the analysis. Even we simplify many things already. Of course, if you cannot, you are not in this situation, you don't find yourself being able to simplify to this system, then you have even more complication. But even when we simplify to here, you will still see that this is 2 plus tau. So if the term is small, it is a little tricky. Okay, then we introduce some space, the H1 with mean 0, and the dual H1 minus 1 with a so-called mean 0. Okay, so-called mean 0 as the dual of that. Okay, and then you define standard bilinear form, and you define the standard Green's operator. Okay, then it is already known, and this part is not my work. This is already known by Chen and some other actually them, and then they also have some other works later in 2020 something to have some new updates. But this is I think I forgot, is it 2001, 2006? I forgot the time, but it is early 2000. And so they can establish a weak solution. And as you can see, the first term, the first weak equation looks very much like an elliptic kind of thing, even though, like I said, it is not really that nice. You can imagine that it is almost like that. Okay, and then you have the parabolic kind of estimate on the second guy. Looking, I mean, they look like that. Again, it is tricky to say, and it's not entirely true. Okay. All right, and then you also have, these well-postedness, and then you also have some of these control, initial data control. For instance, you propagate from 0 to t, the E term, the subtraction I minus pi of S1 minus S2 will have the exponential bound, and then the pressure difference will have these bound. And now you see is where the funny thing goes in, the inequality on the second guy. You see that you have the integral from phi1 minus phi2 S1 minus S2. And if you remember, it is quite nicely monotone, like what we said, but you see degeneracy. So this is where the tricky part comes in. Okay, now how do we do data assimilation? The way we do it is we take an interpolation operator that comes naturally. When we do the computation, we are going to pick finite element space, and what we did was we take some standard discontinuous Galerkin space, and then we just flip it as the extension operator. So the natural candidate for interpolant will be a coarse grid to fine grid interpolation, and then the dual operator will be the extension. You can take many kind of examples. You can do the Fourier mode projection extension. You can do some of those spectral elements and trim. and then you take the first field and then you flip it. So there are many ways you can do. You can do volume elements. You can do some of these polynomial interpolation. And like what we said, we do piecewise constant. I didn't say piecewise constant, but I just mentioned finite element interpolation when we flip it. Okay. Then the model we have will be the following. So we now have our data assimilation model with the previous term that we were talking about. But of course, because as you see, global pressure is kind of artificial. Okay, so some will dispute whether it is physical or not, but they are somehow artificial because we brute force taking some of these coefficient functions that represent physical parameters, and we just brute force integrate them, brute force do some combinations. So we do not really expect measurements of global pressure term. Okay, otherwise some people will say it is cheating. Of course, like I said, whether it is not true to say that we indeed still have some global pressure physically relevant or not, it is up to debate. But from the mathematics, we somehow think, okay, it doesn't make much sense. So what do is we only feed back part of it, which is the saturation term. So we assume measurement on a coarse mesh or on some coarse mesh with respect to that finite element, of course, space that you can measure. And that makes sense if you think of the meshing as arbitrary, because your coarse mesh can be with a different shape and with some of these interface that goes along the physically relevant media that you can have. So it is not that nonsense, because so perhaps you think, okay, I give you a finite element space and then I do measurements along the finite element space. It seems artificial, but actually we have the degree of freedom to choose of coarse mesh finite element space, and you can choose them so that they can be physically relevant. So this is how you can do that. And then our results goes like that. On the theoretical side, that we also have the well-postness. Compared to the original well-postness, this is not super difficult to tricky, but we will get the convergence. So the convergence is funny because the convergence in the end will be the new saturation term that you want to feed back in, will be controlled. But because of the way that things are chopped, so as you can see in here, you now have the mean term, and then you have the term that is without mean. The two terms will be slightly having different bound, and the mean term is nice because turns out the mean term is just a conserved term. Okay, the Q norm is conserved. Okay, and well, I shouldn't say conserved, but I mean it's just exponentially decay in a very nice manner, and so you can write a very nice ODE equality to that, and then in that sense it's conserved. Okay, but you will get a decay of the guy that you subtract with the mean, and then you have the propagation all the way down, and the difficult part will be, to be honest, again coming from this guy, the second term in the left hand side of the inequality, because you have monotonicity but you do not have very nice monotonicity. You have the tau power in there, and because of that we will have to have some cutoff so that we can only say that until we hit some noise level it works. Okay, so we define a large T so that the S minus S tilde norm, a particular kind of LP norm with the nice power that we choose with the tau in there, okay, is still outside the threshold of h to the power 2 plus tau, then you can bound it. Once it enters the noise region, we cannot bound it. Okay, and the idea is, to be honest, getting just some chromo type inequality working. And you play the trick, you do the subtraction, and then you bound the elliptic. I mean, again, don't dispute whether it's elliptic or not, but I almost imagine that it's elliptic, so because it's the same kind of technique. So the first equation, you bound it similar by the elliptic trick, and then the second term, you bound it using the monotonicity, and you throw everything at the right-hand side, then you get something like this. Very similar to the inequality you get in here, okay? Except, like I said, the tricky part will be phi tilde minus theta tilde minus theta and s tilde minus s. Okay, and this will be the term that will cause all the trouble. So we absorb that by monotonicity, strong monotonicity, but with the tau, and then we get inequality like this, and everything else works nice. But the problem is how to absorb this term. So it is impossible because, to be honest, if the guy is small, you cannot absorb it. This violates mathematics, basic understanding of mathematics. So what we can do is we can only put a particular threshold so that unless they are in a very small neighborhood, we can get their data fidelity all the way going down to almost the error term. Okay, and this is where what we can do about. So we put a particular trimming with a particular time t, and then unless we get into this threshold, this whole inequality works with the term that is more than quadratic will be replaced by the quadratic. Okay, and of course there will be some power and some numbers, but the major issue is replacing the 2 plus tau by 2. Okay, and once you get that, then everything else is chromo inequality, chromo type inequality. So it is not super tricky, but again, the tricky part will lie in this monotonicity. And that is, to be honest, one of the major reasons we take this model to test, because for Navier-Stokes and Euler, they don't have super nice behavior. Well, okay, 2D, yes, you have nice behavior, but in general, people are still thinking whether they have nice behavior or not, and these are difficult problems. On the other hand, you can have some very nice problems. In those cases, when you just have very nice parabolic equations or things like that, then of course you expect everything's nice and well posed. Okay, so this is a marginally nice enough, but not so nice term that we can prove something, but we also have to test numerically to see whether it makes sense or not. And that's one reason we choose that. You can, of course, just numerically try multi-phase flow, and the numerical technicality for two-phase and multi-phase are not that different. Okay, yeah, almost not that different, but theoretically speaking, it is tricky. Okay, so what we will do is we will test it numerically. So we test it with the domain, and the way we put it is Neumann boundary condition. And again, you can dispute whether it makes sense or not. In fact, you can put a boundary condition that is not Neumann for the model. You can just even let it free. Some people do these free boundary and stuff like that, but you can do whatever you want in there. Numerically, the major thing now is to test whether it works or not. Okay, so we are having the profile, the ugly profile like this, which is one of the profile that people use for these multi-phase computation. Sometimes with perhaps the background with some jumps and so on and so forth. Okay, and then we have some source term and some the source term of Q and W. and we test it with several cases. First, we do that with full domain, coarse data with full domain, and then we do the case with half of the domain, and then the third one will be just, the third case will be just no data taken. When this have no data taken, it just means you now have another crazy initial data that you don't care, and then you just run it. Then of course it satisfies the whole PDE setup, but it is not physically relevant. And then we get some convergence. And as you see, the one with the full and the half data will all having the error converging. The one that of course without data fidelity term will just stay above. So the blue guy is just there. But when you have measurement of the full data, okay, then it is expected to be converging nice. Of course, that's happy. Okay, but the case with half of the domain, then people will dispute, okay, whether it makes sense or not, and we don't have the proof, but numerically it works. So we can show this. So you can start, so the bottom are the errors, by the way. So you start with this two-phase flow with this boundary, and then you just start moving, and then you keep moving, and then this is this is t equals to 0.1, and then so first case with full data, and then yeah, half of the domain. So you can see in here, this is half of the domain. Okay, this is chopped in half of the domain. So count top, left, middle, 1, 2, 3, 4. Okay, the third picture is the half of the domain. Okay, and then the last guy is just for comparison because we don't fit in any data. Okay, this. Okay, then you solve it, and then you start realizing that the measurements start to fit in and force the term to start going like what is the left. The left is the exact solution. Okay, so okay, so again to clarify, the left one exact solution, the second guy is the one with the coarse mesh data fidelity feed it back in. The third guy is the one with half of the data feed it in, half of the domain, and we choose it on one side. So we expect things to propagate on the other side, but we don't have nice proof, but we should test it because, to be honest, physically relevant cases should be like that. We should not expect we can sample everywhere. Okay, and then the last guy will be having nothing, so error will just be everything. Okay, you can imagine, because the last guy, the fourth guy, is just solving it, right, and without any reasonable initial data. So we will just be a solution that has no relevance to what we are solving. Okay, so that's how you interpret it, and the top four pictures will be the solutions. The bottom four pictures will be the errors. Okay, so t will, of course, when t is equal to 0, nothing interesting to see, but starting from t equals to 0.1, you already start seeing that the data fidelity are coming into play. So it's feeding back in. Okay, and then now slowly entering the situation of now that it starts to be more physically relevant when t equals to 1. The third guy that you see in here is still not that nice, because of course we just fit in half of it. The guy that is on the left is nice. Sorry, the second guy is nicer, of course. The fourth guy is irrelevant, to be honest. Okay, but of course, the fourth guy will still have some exponentially decaying term, because the guy in the end will have some exponential decay. So, but that is entirely irrelevant. Okay, then when t equals to 10, you start seeing that the physically relevant term start to come up, and the second guy looks more like the first guy. The third guy is still so-so. Okay, but when it comes to t almost equal to 100, then they match up. And nicely, both of them match up. So whether it is full data fidelity or half of the data fidelity, they all match up. Again, the last picture is irrelevant, just to show that, in fact, you know what, even if we don't feed it back into that, our PD is not so terrible. So they always have some exponential decay. So error will always decay, but it is not relevant because, as you can see in here, you can compare the convergence rate. Okay, so the blue guy will be there, but it's not relevant. Yeah, it's just to show that. So the major pictures of interest will be this second and the third in the middle. Okay, and that will be it for my presentation. And some of the later work will be perhaps more complicated model, of course. And oh, by the way, we are using the discontinuous Galerkin spaces. So perhaps if we take more complicated models that we should introduce jumps and so on and so forth. I think that this kind of idea can be tested. Yeah, and thank you.